Hi everyone. Today, I am going to present our work at CVPR 2024 on deep generative model-based rate distortion for image downscaling assessment. Image downscaling is a fundamental problem in image processing and computer vision that focuses on preserving information present in the high-resolution images, which is especially important for applications and devices with limited screen spaces like smartphones and iPads. To date, researchers have developed many sophisticated approaches like bicubic, bilinear, nearest neighbor, DPID, perceptual and L0 regularized. Nevertheless, research in image downscaling algorithms has significantly slowed down due to the lack of a quantitative measure to evaluate them. To fill this important gap, in this work, we propose a novel image downscaling assessment by rate distortion, IDARD, measure to quantitatively evaluate image downscaling algorithms. In a nutshell, the main idea of our IDARD measure is that a superior image downscaling algorithm would try to retain as much information as possible in the LR image, thereby reducing the distortion when being upscaled to the size of the original HR image. To achieve this, we create a proxy task, namely the lossy compression problem underpinned by Claude Shannon's rate distortion theory, and formulate image downscaling as its encoding process. In this way, the decoding process is formulated as image upscaling, which is also known as image superresolution. In the equation, X is the set of input high-resolution images, X hat is the set of output reconstructed images, R is a rate constraint determined by the downscaling process, Q is the probability density function, PDF, of reconstructed HR images X hat conditioned on an input HR image X with respect to a given lossy image reconstruction function F that F is implemented with successive image downscaling and upscaling functions. DQ is a distortion metric between two image sets where the image correspondence is determined by Q. This equation aims to achieve the infimum of the distortion between input images and their reconstructed versions obtained by applying image downscaling and upscaling successively, which is consistent with our main idea. Therefore, we propose to use the expectation of the distortion as an evaluation metric for image downscaling, which is our IDARD measure. The lower S, the better the downscaling algorithm FDS. The figure below is an intuitive illustration of our IDARD, where FDS denotes the image downscaling method to be evaluated, FUS denotes the image upscaling method to reconstruct the input, and the orange box on the right shows the expectation used in IDARD. Although straightforward, the application of such a metric remained a challenge as it requires a strong upscaling function FUS that can not only reconstruct the input image regardless of the input downscaling algorithm, but also generate a conditional distribution of reconstructed images for each input. Combining these two requirements makes the desired FUS an extremely challenging many-to-many mapping problem that has remained unsolved for decades, resulting in a data scarcity challenge. Our key insight is that such a challenge can be overcome by the recent successes in deep generative modeling. And in this work, we show that FUS can be implemented using existing image superresolution methods like Pulse, SRflow, and others. We demonstrate the effectiveness of our IDARD measure with extensive experiments on both synthetic and real-world image downscaling algorithms. For synthetic image downscaling methods, we simulate the effects of different downscaling methods by adding controllable degradations after bicubic downscaling, like Gaussian blur, Gaussian noise, contrast increase and decrease, image quantization. It can be observed that our IDARD measure works as expected. That is, the stronger the degradation, the worse the downscaling algorithm, and the higher the IDARD, which demonstrates its effectiveness. We further demonstrate the effectiveness of our IDARD measure on synthetic downscaling algorithms across different scaling factors. It can be observed that, the larger the scaling factor, the more the information loss, and the higher the IDARD, which further justifies the validity of our IDARD measure. We also apply our method to compare 6 existing downscaling algorithms, consisting of 3 traditional methods, bicubic, bilinear, nearest neighbor, and 3 state-of-the-art methods, DPID, L0 regularized downscaling, and perceptual downscaling. Note that our method can also evaluate the unknown downscaling in div2K and camera-captured LR images, which shows that camera-captured LR images do lose less information. Please see our paper and GitHub repo for more details. Thank you for watching.